Okay, hello. I will present my work entitled Direct Profilometry, a low-cost 3D acquisition system. My name is Arwan Ahmad Khairuddin. I am from Indonesian Institute of Sciences, or LIPI, or Lembaga Ilmu Pengetahuan Indonesia. And this work was presented in IEEE SICE International Symposium on System Integration 2015 at Meiji University in Nagoya, Japan. Okay, so I think all of you know already about 3D, and maybe some of you already used the 3D application already. Maybe for 3D printing, 3D drawing, modeling, or maybe a 3D acquisition system. 3D acquisition system has been used in various applications, and here I show you some examples of how it is used. Where it is used, for example, in fabric defect detection, so to detect the uh, wrinkles on the fabric, for psoriasis lesion assessment. So this application is used to know the severity of the psoriasis or skin wrinkles assessment. So when you grow old, you get wrinkles in your skin, and also in solder paste inspection. Um, because we have smaller and smaller electronic devices, so this application is important because now solder paste is not like we commonly solder the components, electronic components, but because of the small components we have now, then the solder must be printed first onto the PCB, and then the components will be placed and then sent to the oven to get the heat and to make the solder paste to be melted and attach the component to the PCB. So for the solder paste inspection, yeah, this application is getting more and more important to know especially to know the volume of each solder paste. Yeah. Okay, I will not explain too much on this part. You can find more information about this at the other sources. Okay, so there are some 3D acquisition methods, and here I will only show you the active methods. The first method I will present is the laser triangulation method. So we have camera to capture the object as well as the laser illumination. Usually we use the line laser, and some application they use point laser, but most application use line laser. So how they do it, they sweep laser onto the surface, and then the camera will capture the illumination, and because of the surface profile, then the laser will be deformed, and okay, the camera will the processing device or computer will transform the deformation of the laser into the height information. So because we have to sweep laser onto the surface, then the acquisition time will be long, but we have enough accuracy, high accuracy. Okay. Second method is the fringe projection profilometry, and instead of having laser, here we have projector. And the advantage of having projector is that we have single shot acquisition. So rather than sweeping the line of laser into the object, then we can have single shot acquisition to cover all the object, all the parts that we need to inspect. However, the drawback of the fringe projection profilometry is that it is very sensitive to the environment lighting. So it will be better to use this fringe projection profilometry inside the closed environment. So because we have single shot acquisition, then the acquisition time will be very quick, and we have close to laser accuracy, and sometimes like comparable to laser. Okay, so this is the details of the fringe projection profilometry. So we have camera, projector, computer, and then this is the object, and we have reference plane. And first we generate a fringe pattern from the computer, and then we transfer the fringe pattern into the projector to be illuminated, and due to the object surface profile, then the fringe pattern will be deformed, and the camera will capture the deformation and analyzed by the computer. Okay, most methods use sinusoidal patterns. So this is sinusoidal, I think. Yeah. But due to noise, color response, intercolor crosstalk, and optical aberration, then this camera will not capture the perfect sinusoidal. Yeah. So due to noise, etc., then unperfect sinusoidal will be captured by the camera. Okay, so this is the comparison of the deformed signal model. Yes, this is we call it deformed signal. The signal acquired by the camera in the presence of the object is deformed pattern or deformed signal. So we analyze some methods. First is phase shift profilometry, Fourier transform profilometry, wavelet transform profilometry, inverse function analysis, and spline inverse function analysis. And the signal in phase shift, Fourier transform, and wavelet transform all are modeled as a sinusoidal wave. So the equation in the algorithm or the equation in all three methods are derived from sinusoidal patterns. And in the IFA and SIFA, the signal is analyzed as is, whether it is sinusoidal or non-sinusoidal. Both methods are suited. Okay, so this is the method comparison. Yeah. Previously, we compare the model, how they model the signal. Now we compare the method. So phase shift profilometry captured 3 illuminated reference plane. So from here, the projector project the reference plane without the presence of the object. Only the reference plane, then it is called as reference plane. So captured 3 plus illuminated reference plane and 3 plus illuminated object. And the algorithm then compute using arctangent, and then because it uses arctangent, then the phase will be wrapped between minus pi to pi, then it needs to be unwrapped, then it mapped to the height information, so we can get the reconstructed object. So for Fourier transform profilometry, it only need to capture one illuminated reference plane and one illuminated object, and we find the Fourier of the DP, or the deformed pattern, and the reference pattern. I'm sorry, for all of this we analyze line by line. so it's not all the yeah, except for 2D. We have by default we have 1D. This one. What I mean, what I explained is 1D. 1D Fourier, 1D phase shift, and 1D wavelet. Okay, so and then we extract the fundamental frequency of dp and do the inverse Fourier and unwrap and then reconstruct the object. Then for wavelet transform, it needs only one reference plane and one illuminated object. Then we extract the wavelet coefficient. So we extract in the scale of 64 plus. And then find local max of wavelet coefficient in each position in each scale, and then do phase unwrapping and then reconstruct the object. Okay, next for the inverse function analysis, we capture one illuminated reference plane and also one illuminated object, and we do polynomial fitting of the deformed pattern, and then inverse of the fitted function compose reference plane with the deformed pattern, and then we reconstruct. And for spline inverse function analysis, we capture one illuminated reference plane, then only one also illuminated object, two spline fitting inverse of fitted function compose reference pattern with deformed pattern and reconstruct object. Please notice that in the diagram I put yellow color, so the one with yellow is actually the part that needs the high computation. So from here it needs all methods need some high computation, like for example in these methods it needs phase unwrapping, all needs the high computation. And here in wavelet transform profilometry it has two parts that needs high computation, and in IFA it has one, but in SIFA it has none. So all process is a low cost. Okay. However, in spline inverse function analysis, it suffers from overshoot fitting. This is overshoot fitting. For example, this is the function to be fitted, and if we have noise, then for example in the peak we have this noise, so that the value will change from here to here, then we will have this error, this oscillated error, and this small oscillated error actually will cause the big error in SIFA. Okay, so we propose this method named direct profilometry. So here is the diagram of the 3D acquisition system. Okay, so okay. Rather than using sinusoidal pattern, we will use the linear pattern. So the projector later on will project the linear pattern onto the reference pattern as well as the object, and here the distance between the camera and the projector is d, and then the distance between pair projector and the camera is l, and here the ray that come from EP will be reflected onto the camera from point A without the presence of the object, but in the presence of the object, the same ray will be reflected onto the camera from as it is from point C. So we have two triangle here, so we can use the Thales theorem to compute this H information on this point D. So from the height information can be calculated by this equation. Yeah, AC XA minus AC times L divided by D plus XA minus AC XC. Okay, when we mention this XA minus XC as UX, or maybe we can call it as a shift function, then we can formulate as the shift function times L divided by D plus shift function. Okay, and if each line of the RP reference plane and the reference pattern and the deformed pattern denoted as Sx and dx, then we will have Sxa equal to dxc, and dxc equal to Sxc plus shift function, and the shift function will be, in our equation, shift function will be dx minus Sx divided by dm, where m is the one line that the sorry the gradient. Yeah. The m is the gradient of the each line of the one line in the reference plane, reference pattern. Okay, so basically the direct profilometry is like this. So we capture one illuminated reference plane, and then we capture one illuminated object, and then find the gradient of the reference plane, reference pattern. So we just take one line, single line of the reference pattern, and then find the gradient, and then we subtract the different deformed pattern with the reference pattern and divide with the gradient. So we just subtract this one, this image with this image, and then we divide with the gradient, and then we map with this equation, and then we will get the reconstructed object. Okay, for the simulation, we use a parabola as an object because this parabola has two unique properties. It's smooth in the middle and sharp at the edges. So this will be the linear pattern, and then this is the deformed pattern. So you see this, there is parabola here. And for the simulation, we add the noise. We add some noise. We add additive white Gaussian noise, and the standard deviation of the AWGN is varied from 1 pixel to 4.5 pixels. Okay, so this will be the result. With the linear profilometry, we can still see the parabola, and while if we use spline inverse function analysis, the error is too big, so we cannot see the parabola here. And here we use this is for object with white Gaussian noise of 1 pixel. In the 4.5 pixel, we can almost see no parabola here because the error is simply too big. While in the linear profilometry, we can still see the parabola. Okay, so here this is the table where you can see the error in SIFA and direct profilometry, and this may be the easiest diagram for you to see the comparison between two. So you can see this is the log of the standard deviation of the error. So the SIFA is very big, while in deformed pattern direct profilometry is or linear profilometry is quite small, whether on the filtered and non-filtered. Okay, so here we built a prototype, system prototype. We use Canon EOS 70D and Optoma Pico projector, and this is the object. And because here we have shadow, to minimize the shadow, to actually we will not have problem with the shadow, but uh, uh, still can reconstruct the shadow part, but we want to get more information, to cover more information from the object. So we move this projector from the right part and to the left part, so the right projection and left projection, and we get this reconstructed object. Okay, so conclusion. A method with low-cost computation for 3D acquisition system named direct profilometry or linear profilometry has been proposed. Using a linear pattern, no monotonic extraction or unwrapping are needed. Thus, the computation cost is very low. And because no oscillation of error as in IFA and SIFA, our proposed method produces small error on the final reconstruction. And from our experiment, it is shown that our algorithm works very well on complex objects, even when shadow occurs. Okay, thank you. Hope you can get benefit from my presentation, and I wait for your comment. I apologize for my English and for my if if my presentation does not satisfy you. Yeah. Thank you once more. See you in the next presentation. Thank you.